All right, so I wanted to start today by going back and looking at something from what we were looking at the end of Friday's session. We were looking at nomenclature in particular, and I wanted to take this opportunity to just kind of rehash some of the stuff from nomenclature, because I know that that was one of the topics that was of higher difficulty when it came to the midterm. And so with nomenclature, we have to recognize that we need to be able to do nomenclature in two different directions. We need to be able to look and read the name of a compound and know what the formula for that compound is. That's what this first table is all about. But we also need to be able to look at a chemical formula and figure out what the name of that compound is as well. And that's what the second table is all about. Now, to help out with kind of the construction, I added these columns in the middle. And the purpose of those two columns is basically for organization, just to help you kind of figure out at least a starting point if you're not exactly sure where to go. So, for example, with iron 2 chloride, based on the element and the Roman numeral, I know I'm dealing with iron. Iron is Fe. And the Roman numeral 2 tells me that the charge on the iron is positive 2. And for the chloride, I need to go to my periodic table. On my periodic table, I can see that chloride is a halogen. It's in group 17. Everything in group 17 takes on a -1 charge. So chloride is Cl, and it's got a -1 charge. So to figure out the formula of iron 2 chloride, what I need to do is I need to look at my two ions, and I need to determine, do the charges line up? Are they matching? Am I looking at the same charge, positive and negative? And the answer in this case is no. I've got a 2 charge on the positive. I've got a 1 charge on the negative. That's not equal. When it's not equal, I need to do the crisscross, where the charges become the subscripts. So I need 1 iron from the -1 charge, and I need 2 chlorines from the positive 2 charge. The formula for iron 2 chloride is FeCl2. All right, let's move on to the next one. I've got calcium hydroxide. Calcium is Ca. I look on the periodic table. I see that Ca is in group 2. So it's going to have a positive 2 charge. And now I come up to hydroxide. Hydroxide is a polyatomic ion. So we had a list of polyatomic ions that we had to familiarize ourselves with. From that list, we would be able to determine hydroxide is OH -1. Now, when it comes to polyatomic ions, can't always give you a good hint. But one thing I can tell you, if the name of the ion ends with that IDE suffix, one thing that I can tell you is that you can figure out its charge based upon the periodic table position. And how you do that is, I look at hydroxide. Hydroxide is the combination of hydrogen and oxygen. Hydrogen has a +1 charge. Oxygen has a -2 charge. If I put those two charges together, +1 with -2, I'd end up with a -1 charge. And you can do that with anything that ends in IDE. Cyanide's the same way. Cyanide is a combination of carbon and nitrogen. Carbon with a 4 charge. Cyanide or a nitrogen with a 3 charge. Put those together, that's where I get my -1 charge. All the other IDEs, well, those come from elements themselves. I can look at the periodic table and I can say, okay, it's in this group, it's going to have this charge. Coming back, I see that I have a +2 with calcium, I have a -1 with hydroxide, the two charges do not match, so I'm going to have to crisscross again. The two hydroxides, since it is a polyatomic ion, I'm going to put that in parentheses so that I know that it is two hydroxides, it's two OHs, not just two H's or two O's. Look at the third one, sodium chlorate. Sodium is Na. I look at the periodic table, I see sodium is in the first group, so I know it's going to have a +1 charge. Chlorate is on my list of polyatomic ions. It's ClO3 -1. Now, couple of things. If you don't have that list memorized, there are a couple of things that you can kind of pick out that would at least help you get close, if not absolutely correct. So the fact that it ends in ATE, or if it ended in ITE as well, tells you that you have oxygen in the ion. Chlor sounds a lot like chlorine. So I know that I've got chlorine and I've got oxygen. I've got both of them together. The question is, how many oxygens to how many chlorines? Generally speaking, if I'm dealing with that ATE ending, that usually means that there are going to be 3 oxygens. Now the exceptions to that, phosphate, sulfate, and chromate, those all have 4. Those are like the exceptions, not the rule. Everything else, you generally see 3. So, carbonate, CO3. Chlorate, ClO3. Bromate, BrO3. Nitrate, NO3. 3 is more the rule than the exception. Where do the charges come from? That's largely positional. Most of them are -1 charge. However, if you slide over to the oxygen group, most of the ones in that oxygen group take on a -2 charge. Most of the ones in the nitrogen group take on a -3 charge. And really, the only exception in that is nitrogen. The nitrate ion is going to be -1 because it's not big enough to have 4 charge. From a standpoint of formula, I can see that the charges match. I have 1 charge here and a 1 charge here. So I don't need to do anything other than just bring these together. Right, I'm gonna skip these other two here, let you work on those on your own. I'm gonna skip the sulfur trioxide. Now, sulfur trioxide, so as soon as I start seeing prefixes in here, that should lead me automatically to this is not ionic anymore. And if I look at the chemical, if I think about what's in it, sulfur is a nonmetal, oxygen is a nonmetal. Anytime I have multiple nonmetals, we're dealing with a covalent molecular compound, it's got a different naming system. So we're not going to think about things in terms of positive and negative. What we really want to do if we're organizing ourselves here is look at the name and try to figure out how many of those there are. So sulfur by itself tells me that I only have the one sulfur. Otherwise, it would have a prefix on it as well. Trioxide tells me that I have 3 oxygens. So if I put those together, SO3 is the color. I don't need to put the 1 with the sulfur because the 1 is assumed. So we'll skip the last one and let you work on that on your own. The answer is in the key that is posted on Blackboard already, so you can check yourself against those. Any questions with these 4 that we went through directly? All right, now if we have to flip it around, we're gonna kind of do the same thing, but we gotta work our way backwards. And so if I look at this first one, I know that I'm dealing with gold because AU is gold. But I also look and I see AU, the transition metal. Transition metals can have multiple charges. So I can't just stop at calling this gold. I'm going to need a Roman numeral to go with it. Now, if we're following along here, the other ion here is NO3. And we put together just kind of, again, the basics. If you don't know what this is, you can make a pretty good guess of it based upon what it's made out of. It's nitrogen and oxygen, so we know it's going to end in either ATE or ITE. And our general rule of thumb is that if there are 3 oxygens, it's ATE. So nitrogen and oxygen nitrate is going to be the ion. So just off of a guess, based upon kind of most common themes, you could come up with nitrate this way. Based on the fact that it's going to either end in ATE or IT because it's got oxygen in it. Because there are 3 oxygens, most commonly that means 8. Now, gold nitrate is partially correct. But again, without the Roman numeral, without the telling of charge, I can't read gold nitrate and know that it's AuNO3. I've got to have a little bit more information. Now, nitrate is a -1 charge. And since there's only 1 nitrate and only 1 gold, we know that the charges have to match. That means that the gold has to be a +1 charge, which would make its Roman numeral 1. So the full name of this would be gold 1 nitrate. All right, look at the second one here. In this second one, I know I have CO. CO is cobalt. I look at the periodic table, I see cobalt is smack in the middle of the table. So it's a transition metal as well. I'm gonna have to identify its charge. I can't identify it right now, but I know that it's with oxygen. And here's the thing. Oxygen is the only non-metal here. So this isn't a polyatomic ion, it's just oxygen by itself. Anytime you have an element by itself, we know that we are dealing with an ide for the ion, and the oxygen version of that would be oxide. I look at the periodic table, oxygen's in group 16, elements in group 16 have a -2 charge. And so since we have a 1-to-1 ratio of the cobalt and the oxygen, I know that the cobalt's going to have a +2 charge, which means that this is going to be cobalt 2. So I put those together, cobalt 2 oxide. Questions with either of these first two? Okay, let's do a covalent example. Let's do NO2. So here, since we have the formula, we just need to look at it, identify the elements, put on the proper prefixes. So the first element is nitrogen. And there's only one nitrogen. What is the prefix for 1? It's mono. Do I need to put mono on the nitrogen here? In this case, no. If the first element is 1, we can leave it alone and just assume the 1. The second element is oxygen. We have to give it the IDE treatment as well, so it's oxide. But there are 2 oxygens. What's the prefix for 2? Di. So put the prefix on there. Now I can put those together. Nitrogen dioxide would be the column. Any questions with any of these nomenclature problems? Okay, now that you've had a chance to kind of rehash and look through that first half of the semester again, are there any questions, any problems on this first half study guide that you'd like to go through more fully before we move on to the second half study guide? Right, hearing none, I'll remind you that that study guide and the key are both in Blackboard in the final exam prep folder. Also in that folder is this study guide for the second half of the course. And so just wanted to remind you of a couple of things and also inform you of some others. So if you remember, the topic that kind of bridged spring break with us was solubility rules and ionic and net ionic equations. And it all kind of centered around what you're eventually going to work on in lab, that 9 bottles experiment where you had to put all those different drops in the well plates and see what reacted and all that stuff. So I made the personal decision to leave off because we kind of just abandoned that entire concept after doing it. We never really came back to it. We never really applied it other than in lab. So solubility rules, what dissolves in water and what doesn't dissolve in water, that is going to be featured in the exam on Wednesday. Now, I've included a question about that in the study guide here. But doing the ionic and net ionic equations, breaking things apart and crossing things out, identifying spectator ions, I've left that off. That's not going to be something that you will see on Wednesday. Don't spend your time studying that particular concept. It's not going to be there. And it's not even in the study guide itself, just to kind of reinforce that point. But aside from that, most of the stuff that you see on this list is stuff that we've been doing over the past month and a half or so. We're talking about stoichiometry. We're talking about limiting reactants. We're talking about the Lewis dots and drawing structures. We're talking about solution stuff, gas stuff, acid-base stuff, and a lot of calculations. This second half of the semester was very, very calculation heavy, with the exception of when we did electron configurations and the molecule drawing. Aside from that, we've basically been calculator junkies for the past 5 weeks. And so the study guide itself is shorter, but it does reflect that. So getting into the study guide itself, you can see very similar kinds of things to what we saw in the last 2 exams. So you go through this and you kind of take what we did in exam 2, take what you did in exam 3, kind of hold them side by side. You're going to see a lot of similarity, which is why I would encourage you, especially for those last 2 exams, use them as resource information, use them as study information to help you identify and understand what you need to do and how to do it. But balancing equations, identifying them by type, predicting the products of double replacement reactions and doing the balancing of those, doing stoichiometry and percent yield kind of stuff, doing general stoichiometry stuff here without limiting reactants. Here's some stuff about solubility rules. Here's some of the stuff that we did kind of at the beginning of this second half of the semester, getting into the electron configurations and the Lewis structures, electronic structure, remembering some of that stuff about orbitals and sublevels, energy levels, that kind of thing. And then getting into a lot of calculation stuff. Calculating by mass percent, calculating by molarity, calculating dilutions, identifying acids and bases based upon reactivity, which I will tell you was probably, for exam 3, that was probably the thing I was the most pleased with, was just how many of you got that information and were able to do this kind of question and do it successfully. Calculation tables, very similar to what we just had on exam 3. Being able to do solution stoichiometry or titration kinds of calculations using that titration equation. Being able to convert in gas laws and use the gas laws appropriately. And then doing some simple stuff with gas reactions and the ideal gas law. So since we only have about 20 minutes left here, I think it probably makes sense to kind of go through the stuff that is the least recent, and maybe the most technically hard to do kinds of calculations. And so I'm going to skip this part here on chemical reactions. In time, most of you have started to kind of pick up on what the differences are between single replacement and double replacement, being able to identify decomposition, balancing equations properly. So there is, like I said, there is a key to this. And so if you do these on your own and you find that you are not doing it correctly, feel free to reach out to me. Remember, we have an open study session tomorrow at 2 here. So if you're going through and starting to review and you realize I'm not getting these right, I need to maybe ask a question or two, take advantage of that session. But let's look at something like this. How do I predict the products of a chemical reaction, in particular of a double replacement reaction? This was something that you were asked to do in exam 3, only you were asked to do for an acid-base reaction, which acid-base reactions are double replacement reactions as well. They're just dressed up a little bit different. Now, the way to set this up is by recognizing that in a double replacement reaction, the charges do not change. So I can look at the periodic table and I can see, okay, calcium is in group 2. Group 2 ions are +2. Fluoride is a halogen. It's in group 17. All the halogens are -1 in charge. Magnesium is in group 2. It's a +2 charge. Sulfate, oh wait, sulfate's a polyatomic ion. Can't use the periodic table to figure it out, but I can use the fact that the magnesium is +2, and the magnesium and the sulfate are in a 1-to-1 ratio with each other. That should tell me that if the magnesium is +2, sulfate must be -2, because otherwise we wouldn't have this 1-to-1 formula. It would be 1-to-2 or 2-to-1 or 2-to-3 or whatever. The fact that I have no additional subscripts here tells me that the charges match. So if I was able to determine that magnesium was +2, that means that the sulfate had to be -2 because they have to match. This is double replacement. So my cations, the positive ions, are going to switch places. Calcium is now going to go with sulfate. Magnesium is now going to go with chlorine. Now, since this is double replacement, the charges don't change. So if calcium was +2 before, it's still +2. The sulfate was -2, it's still -2. Since the charges are balanced, since they match, I don't need to do anything further. The formula for calcium sulfate is CaSO4. Now for magnesium chloride, the magnesium was +2, so it stays. The chloride is -1. And so now we recognize, okay, there is a mismatch of charge. I need to cross them up. And by crossing them up, I'm going to get a 2 here on the chlorine to give us the correct formula. And when I do that, I also come to the realization that Once I've got the formulas fixed, equation's already balanced. I had one calcium on each side, I had two fluorines on each side, I had one magnesium on each side, I had one sulfate on each side. Everything's already balanced. I don't need to do anything further. This is the most difficult part of this particular kind of exercise, is because if you don't get the chemical names, the chemical formulas correct, there's no way that you can balance it properly. So taking those couple of minutes and stopping and looking at the charges and making sure that the charges all are even on both sides and they all make sense, that's going to help you a lot for doing these kinds of problems and giving you a chance to balance them correctly. All right, questions with that example? All right, let's move on to the stoichiometry. Because this is, in general, this is kind of one of those fundamental concepts that if you get it, you get it. And if you don't, it kind of buries you because there's a whole lot of stoichiometry happens. So the question here is about limiting reactants. I have 35 grams of magnesium nitrate and 29 grams of water to make magnesium hydroxide. What is the limiting reactant? And then part B of this is, what is the mass of magnesium hydroxide that can be made from those ingredients? So there are a lot of ways to approach this problem. What I would say is probably the easiest way to approach this problem is if I consider parts A and B together. Because I could answer a limiting reactant problem by figuring out how much product is made. Remember, we did this in class. We talked about making cheeseburgers. Talked about making s'mores. The way to do this is we figure out how much do I have, how much can it make, and what ends up running out first. It's the same thing here. If I try to figure out how much magnesium hydroxide can be made from both of those reactants, the one that makes the least is my limiting reactant, and the amount of magnesium hydroxide it makes answers question B. So regardless of the method I choose, I'm going to end up having to do two stoichiometry problems. It's just a matter of how do I want to set it up. So give myself a little more space here. My scheme, I need to go from grams of reactants to moles of reactant, regardless of which one I'm looking at. I need to turn the moles of reactant into moles of magnesium hydroxide, and then turn that into grams. So that's the process I'm going to go through for both of these. So starting with the magnesium nitride, 35.0 grams of magnesium nitride. First thing I need to do is convert those grams into moles. Anytime I need to do that, I need to go to the periodic table, figure out the molar mass. 3 magnesiums 24.31 each, plus 2 nitrogens, 14.01 each, is 100.95 grams per mole. My grams cancel out. Now I go to turning moles of magnesium nitride into moles of magnesium hydroxide. For that, I need to balance chemical equation. 1 magnesium nitride makes 3 magnesium hydroxides. And then the last step, I need to turn the magnesium nitride, the moles of magnesium hydroxide into grams. For that, I need another molar mass. So magnesium is 24.31. There are 2 oxygens, so 16 for oxygen times 2. And 2 hydrogens, 1.01 for hydrogen times 2 as well. 58.33 is the molar mass. If I do this calculation all the way through, 35 times 3 times 58.33 divided by 100.95, do 3 significant figures, I get 60.7 grams of magnesium hydroxide. Now, is that the correct number or not? We don't know. The reason we don't know yet is because we haven't figured out how much the water is going to make. But for the water, we're going to follow the same kind of process, starting with the 29 grams of water. Going to turn the grams of water into moles. For that, we need the molar mass. Hydrogen's 1.01 times 2. Oxygen is 16. 18.02 grams of water. Second step, I need to turn the moles of water into moles of magnesium hydroxide. 6 waters for every 3 magnesium hydroxides. And then the last step is exactly the same. I need to turn moles of magnesium hydroxide into grams. Since we already calculated that molar mass, 58.33, we can reuse it again here. All that's left is the calculating. 29 times 3 times 58.33 divided by 18.02 divided by 6 to 3 significant figures is 46.9 grams of magnesium hydroxide. So what this tells us is okay, the water makes less product. And since the water makes less product, the water is the limiting reactant. So now we've answered question 1. For the answer to question 2, we already did the calculation work. The mass of magnesium hydroxide is going to be 46.9 grams because that's how much the water can make. And then the final question in this set has to do with yield. If we run the experiment and 10 grams of magnesium hydroxide were collected, what is the percent yield? We have to remember that percent yield is actual over theoretical times 100. The actual is what we got in the experiment, so that's 10 grams. Theoretical is what we calculated, 46.9 grams. Multiply by 100 to turn the fraction into a percentage. 10 divided by 46.9 times 100, the three significant figures, is 21.3%. So if we're looking at problems as far as the exam is concerned, you know, what kinds of things can we get into that might give us a little bit of trouble? What might be what you call the quote unquote hardest question on the exam? It's probably something along these lines, where you're gonna have to do some kind of stoichiometry, some kind of calculation work to figure out something, you know, on the bigger side of things. But if you kind of follow just general straightforward principles here, this isn't that bad to do. It just is time consuming. So you can bet that if there is a question like this, there's only going to be one question of this kind on the exam, because it's going to take you a while to do it. It took us, you know, about 10 minutes walking through it, step by step. All right, so that's where I'm going to stop. That's kind of where we are right now. Again, let me remind you, study session in here tomorrow at 2 o'clock. It's open to everybody. It's just a place to kind of sit and study and get individual help from me. It is not a formal study session like this. So there is no Q&A, there is no back and forth. I'm just going to be kind of wandering around and helping people as they need help. Otherwise, I will see you on Wednesday at 12 o'clock here. Have a good afternoon.